Hi, my name is Ranisha Blakeney, and we currently did a project on Cantilever Beams. My partners include Katie Bradley and Adam Bidwell. Okay, I'll first start by explaining the mathematical model we were given. This equation is basically used to find the stiffness of any material. C is a constant that we found in our program, as you'll see later in the PowerPoint slide. E is the modulus of elasticity, and basically this is an object's ability to deform when force is applied to it. W is width, T is thickness, and L is length. By using this equation, you're basically able to find out the stiffness of any type of material, and you basically just plug in the numbers that correspond to that material and the different parameters. For instance, if you have aluminum, you plug in the modulus of elasticity for aluminum, the width of aluminum, the thickness, and the length of aluminum, and you'll be able to find out the stiffness of that material. Okay, so this is our stiffness versus length graph. This is actually one of 4 graphs. We also have the stiffness versus modulus of elasticity, width, and thickness graph. Basically, those 4 graphs are used to find the exponents that correspond to each parameter. We basically just graphed the data and then ran a trend line through it, and the exponent that was in the trend line equation was the exponent that corresponded to that parameter. Okay, so this is our force versus deflection graph in relevance to material. We also have 3 graphs similar to this one, corresponding to the other 3 different parameters. The way you find K from this graph is basically the slope of each trend line, and we use these values of K to find our constant C. As you can see, K does vary depending on the different type of material you use. Okay, so here's a table of our exponents that correspond to each parameter in our equation. As you can see, E and W will both raised to the first power, and T and L were both cubed. Our C value came out to be 0.26, which according to our professor is actually pretty accurate. At the bottom you can see the equation all put together with the exponents plugged in, and you could use this equation to find the stiffness of any material that you were given. Okay, so this is a slide of our summary tables, and basically the purpose of this slide is to show the accuracy of our equation. If you look at our percent differences, they were all about under 20%, which is actually pretty good. Basically what we did was plug in numbers into our equation and got the results from that, and we compared the results of that to the results we got in the lab with those same numbers. The beam that we thought would be the best would be a combination of the aluminum beam and the stainless steel beam. And you first start by placing the turbidity meter, the velocity flow meter, and the nutrient meter onto the aluminum beam. And then you put a portable sampler and the pH electrode onto the stainless steel beam. The reasons why the other beams were not used was because they either weren't efficient enough or they cost more. And the reason why the $4 aluminum beam wasn't used because it just had too much deflection, and the $10 stainless steel beam wasn't used because it wasn't long enough. The $15 stainless steel beam and the $10 aluminum beam were chosen over the $13 aluminum beam and the $20 stainless steel beam because they were more cost effective.